Hello everyone, welcome to Physics Match. Today we will look at a problem which gives insight related to the use of phasors in solving wave optics problems. So let's try and solve this problem. Three coherent point sources S1, S2 and S3 are placed on a line perpendicular to the screen as shown in the figure. The wavelength of the light emitted by the sources is lambda. The distance between adjacent sources is 3 lambda, which is d. The distance of S2 from the screen is capital D, which is much greater than the lambda. Find the minimum non-zero distance x of a point P on the screen at which complete darkness is obtained with respect to the point O. Fine, so there are options given. We will see like how to handle this problem. So what and all one should know before trying this problem? Obviously, they should know the meaning of coherency. Okay, so coherent sources meaning you should know. So whenever we have coherent sources, then we can say that this source S and S dash, let's say they are coherent sources, then their state of vibrations can be related. Maybe their state of vibrations are same when they started, or they should have some constant phase relationship between them. See, in this problem, they haven't mentioned S1, S2, S3, what is the initial state of vibrations or initial phase of these sources. So we always will assume they are all in the same state of vibration or same phase when they are like emerging from the source. And why should we consider that? Because they have not given any information. So we are imagining that S1, S2, S3 are coming from the same original wavefront. So S1, S2, S3 will have same phase. Okay. Now we can treat S1, S2, S3 as coherent sources. That is one thing. Now let's say we have this S and S dash. Suppose if we consider some random point as P dash, the energy coming from S dash will reach the point P. As it reaches, the energy will reach there at certain state of vibration, correct? As it reaches at some state of vibration, then I will be representing that by using a phasor. You know, phasors are rotating vectors. You can imagine that these will be rotating with the frequency of that particular wave. Okay, so I hope you're all familiar with phasor ideas. Now, S dash, if I call it with some color representation like yellow color, when energy reaches this point P dash, then I'll be witnessing that as some state of vibration. Observe, suppose if I represent this point S with some other color, like say S, the energy reaching from this S to the point P dash, definitely this energy will travel an additional distance, right? So this is the additional distance. Okay, so let me call it as delta X. Okay, now this delta X, the additional path covered by this source S, will give rise to a path difference, give rise to a phase difference as 2 pi by lambda. You know, this is the conversion factor between the path difference as well as phase difference. Now, when this energy reaches there, the point P dash, our phasor looks like this. This is the energy coming from S, and this will have an additional phase of delta phi. So meaning the source S would have traveled an extra angle of delta phi in order to reach the point P dash. Why this is happening? Because it is covering some additional distance of delta X. Okay, so this is how we are going to use the phasors, and definitely at the point P dash now, based on this particular delta phi, the intensity or resultant of the amplitude will be decided, and you know, by using vector logics one can find the intensities of that. Okay, now I'll be using exact same logic for 3 point sources. Now let's begin that analysis. Suppose if you look at this one, let me name these things like this, the point P. Okay, and this one is point O according to given data. Now we can extend this particular line all the way to the infinity. I'll be just highlighting this. It can be extended all the way to the infinity. So this is our positive y-axis, let's say. Now suppose if I mark S1 with red color and S2 with the blue color, let's say, and S3 with green color. So actually they all will be monochromatic, same light, but we are writing like that so that we can have some differentiation. Okay, so we will begin this analysis from S3 source, let's say. See, at infinity, at positive infinity, let's say, the energy coming from S3 when it reaches the infinity, okay, then it will reach there at certain state of vibration. Obviously, this energy traveling from S2 to infinity, it will also cover the same distance as that of S3. Then that will be in phase with respect to S3. Now you might be thinking, sir, here there is some extra distance that S2 fellow should travel in order to reach the infinity. But we know this, right? Like it is reaching the infinity. If they are reaching really infinity, they are all covering same distances, right? So we can think that they're all reaching by covering the same distance. So they will be reaching there at the same phase. Okay. And the same thing happens with red color also. It will reach all the way to that infinity. As it reaches this S1 vector, right? That will reach there with the exact same phase as that of the other two. So obviously we can predict now if this amplitude is A, we are imagining non-absorptive medium. So their amplitude remains same. So we can say that these resultant amplitude is going to be 3 times of A and the resultant intensity is proportional to 3A the whole squared. So we can say that intensity of the resultant brightness, okay, intensity of the resultant combination would be 9 times of I naught. So this is what we expect at bright spot, bright fringe or bright spot. Okay. Now this is happening at infinity. Okay. It's happening at infinity. Now instead of talking about infinity, let's now talk about the point O. So this is our interest. This is point O. Now for point O, how things are at the point O. At the point O, what and all we have. See, definitely the energy coming from S3 will travel some distance to reach the point O. So it will reach there at certain state of vibration. This is S3. And S2 will also reach there by traveling some distance. But we know that S2 will travel an excess of 3 lambda. D is equal to 3 times of lambda, right? So S2 will travel an additional distance of 3 lambda when compared to S3 in order to reach that point. So basically 3 lambda meaning what? In relation with S3, S2 fellow will undergo 3 further rotation. It's like 1 lambda corresponding to 1 rotation like this. Okay. So 2 lambda meaning 2 rotations, 3 lambda meaning 3 rotations, and 3 rotation and will again will be in phase when it reaches the point O. So that's what with respect to S2. And energy coming from S1 will definitely reach the point O. But if you think that S1 is covering additional distance of 3 lambda plus 3 lambda, basically 6 lambda, meaning in relation with S3 fellow, this S1 source will undergo a rotation of 6 times because we know that it will be traveling 6 lambda amount of excess distance, 6 lambda amount of excess distance, right? So it's like 6 times it undergo rotation in relation with S3. Suppose if you think with respect to S2, whatever the angle described by S2, this S1 fellow will go additional 3 rounds in order to reach that point O. Okay, so basically S1 will also reach there with the same phase. Now meaning the resultant amplitude, as you can now easily predict that the resultant amplitude at that point is going to be 3 times of A, and the resultant intensity is going to be 9 times of I naught. I am using I naught is proportional to square of the amplitude, and amplitude is for individual source. This is what we are taking. Okay. So there is no confusion with this, I think. Okay. But the question is not to find some bright fringes or comment on like what happens at infinity or at the point O. Now we have to look at the point where this complete darkness occurs. Okay. So how is it possible? Let us take now some random point. Okay. Let me choose some point. Say I'll be highlighting this here, somewhere here. Let me name it as P dash. Okay. P dash is the point which is not exactly infinity, but from it is almost close to infinity. Let's say P dash is almost close to infinity. Now, definitely at P dash, if you observe, we can say that at P dash, S3 will cover some larger distance, meaning some distance to reach the point P dash, but S2 will cover an excess distance when compared to S3 to P. So here we can comment that S1 P dash will travel excess distance when compared to S2 P dash, then S2 P dash will be definitely more when compared to S3 P dash. This is our understanding. Okay. Now let's say at the point P dash, this is point P dash. At the point P dash, we have this energy coming from S3 will reach there. Okay. And energy coming from S2 will also reach there, that blue color fellow. And we'll be writing that somewhat like this. Okay. If this is corresponding to S2 and this one is corresponding to S3, then we can say that to reach the point P dash, the energy coming from S1 will travel all the way to P dash. And suppose if it reaches like this, then observe here one important aspect. In order to reach the point O, we have observed that by the time this S2 reaches this point O, it would have covered 3 rotations. S2 will cover 3 rotations. Okay. S2 will cover S2 will cover 3 rotation in comparison with S3 in order to reach the point O. And S1 will cover 6 rotations in order to reach the point O. Basically, if S2 covers an angle theta to reach a point, then S1 will cover an angle 2 theta to reach the same point. That's what we are looking at, right? So basically, to reach the point P dash, if I assume that S2 will cover an angle of 120 degrees, which we usually write it as 2 pi by 3, then S1 to reach the point P, it will definitely cover an angle of, okay, so I'm highlighting this here. It will cover an angle of 240 degrees, okay, to reach that point. If this happens, what is the benefit for us? See here, we know that all these three fellows are having the same amplitude. You can write it as A and A and A, and they are all like say 120 degrees with respect to each other. So they will cancel each other so that the resultant amplitude would be zero. If resultant amplitude is zero, we can definitely say that they have the intensity at that point as zero. So this is the configuration for dark fringe. Okay, so there is one possibility like this. Okay, now if this is the story, then we will find out what is the distance of this point P dash with respect to the point O. Okay, so P dash from the point O, right? So we will think of that in the another slide now. See, this is S3, this is S2, and this is S1. I will just check. Yeah. Now at some point P dash, the distance it is covering, like say S2 to point P dash, and this is covering some distance, and even this one covering some distance to reach the point P dash. So if I call this angle some angle here as theta, then you can think that this is not exactly theta, it will be theta dash, and this would be theta double dash, let's say, We know that theta dash is slightly greater than theta. Theta double dash is slightly smaller than theta, but even then we will say that it is theta, theta, theta only. Why? Because the distance, right, from S1 to S2, S2 to S3, that distance is very, very small here. So you can consider that approximation when compared to our distance capital D involvement in this. Okay. Now, what is the benefit of this? They have given the distance from S1 to S2 as D, S2 to S3 also D. So if you compare with S3 P dash minus of S2 P dash, then S3 P, sorry, let me write S2 P dash minus of S3 P dash. S2 P dash, that will be slightly bigger than compared to S3 to P dash. And how much bigger? For that, I'll be just dropping one perpendicular here. So this we can write it as d cos theta. So this is the path difference, okay, between second S2 and S3. So path difference between 2 and 3 is going to be d cos theta, okay. And the same thing if you work with S1 to P dash minus S3 to P dash, definitely you can write it as 2d cos theta, because we know that S1 to P dash is greater when compared to S3 to P dash. So this is the path difference between 1 to 3, okay, 1 in relation with 3, okay. So this is 2d cos theta. Now these two equations becomes our important equations, okay. Now let's think at the point P dash. Just now at point P dash we recognized there is a possibility that if S3 fellow reaches at certain phase like this, S2 fellow reaches that point and S1 fellow reaches that point at certain other phases. Now I'll be considering like S2 fellow will be here by covering an angle of 120 degrees. So the path difference between S2 to S3 is 120, and path difference between S3 to S3 to S1 is 240. Why are we taking this? Because if S2 covers an angle 120 to reach that point P dash, then S3 will cover an angle of 240 to reach that particular point P dash. That's our logic. Okay. Now, since we know the path difference, sorry, phase difference now, then we can think of the path difference. Okay. Now, phase difference, okay, phase difference, delta x 2 to 3 is d cos theta, we know. And we also know between 2 to 3, the phase difference. So now we'll try to convert them, lambda by 2 pi times of path phase difference. So between 2 to 3, the phase difference is 120 degrees. It is equivalent to 2 pi by 3 radians. So I'll be writing it as 2 pi by 3 radians. So we can write this one as 2 pi getting cancelled out, lambda by 3. So d cos theta is equal to this, and d is 3 lambda, so cos theta. So we can write cos theta being equal to 1 by 9. If cos theta is 1 by 9, then what next? If cos theta is 1 by 9, then we can write this as theta. This is 1 and this is 9, and we can find this one as 80. So tan theta is going to be root of 80 divided by 1. So from this particular triangle, we can say that this is x and this is d. So I'll be looking at triangle OS2 and point P dash. Okay. So tan theta is nothing but x by d. So x is going to be d times of root of 80. Okay. So it turns out to be how much? We can write this one as 16 times of 5. No, 16 times of 5. It is 4 root 5 times of d. So we'll check, is there any possibility of such an answer? So 4 root 5 times of d, that is available here. So this is a potential answer. But let us think of the question properly. They are saying find the minimum distance, correct? So here p dash is very close to the infinity. So since it is close to the infinity, we cannot expect p dash to be considered as the minimum distance. Now, how do we even think of getting a minimum distance where the dark spot is obtained? So for that, we will do further analysis. Now let us think of this arrangement again. This is S1 and S2 and S3, and this is point O, and this is infinity, let's say. Now we know that between S2 to S3, the distance is 3 lambda from here to here. Between S1 to S2, that is also 3 lambda. Now let's compare only between S2 to 3. Okay, so path difference between 2 to 3. At infinity, this is 0, and path difference between 2 to 3 at point O is 3 times of lambda. So basically, if this is a zeroth bright fringe, then you can say that somewhere we'll be writing it as first bright fringe, and there will be somewhere second bright fringe. Then we'll have here third bright fringe. So this is what happens with respect to 2 and 3. Okay. Now we'll think of 1 and 3. So path difference between 1 and 3, and this will be 0 at infinity. So it is 0th bright fringe between them also, right? Now, if you compare, meaning ignoring S2, only think of S1 and S3, the path difference in reaching the point O would be 6 times of lambda. So basically it corresponds to 6th bright fringe. So meaning in between somewhere we should have some like first bright fringe and second bright fringe. Meaning I'm just randomly writing third bright fringe and fourth bright fringe and fifth bright fringe all the way sixth bright fringe. So this is how it is, correct? Now our plan is, say if you're thinking of this bright fringe formations, okay, as an overlapping, whenever this first bright fringe and second bright fringe both will coincide, right? Meaning bright fringe coming from 2 to 3 and 1 to 3, if they're all coinciding, then we'll get brightness of 9 times of I naught intensity. Okay, so that's what we are looking for. But somewhere we can expect like a dark fringe, and this happens, meaning if it is a bright fringe here, first bright fringe, okay, somewhere we can expect a dark fringe here. This is first dark fringe, first dark fringe. Okay, like that, if you keep observing, there could be a dark fringe here which is close to the point O. Dark fringe which is close to the point O. Now, how do we even find this dark fringe? Okay, now definitely we know that if this point P, if it is closer to the point O, then in order to have point P to be the dark fringe, which will be having X to be minimum for point P. For point P, where X to be minimum, X is minimum, then what should be the condition? See, S3 to point P, it would have covered some distance. Say this is a point P, right? S3 to the point P, it would have covered some distance. So we can say that from S2 to the point P minus S3 to the point P would be equal to 2 lambda plus some additional length. Additional length. Now, remember, if this point P, if this point P is coinciding with the point O, then this additional length becomes lambda. Okay. So the path difference becomes lambda between 2 and 3 source. Suppose if you think of S1 to the point P minus S3 to the point P, it is going to be 5 lambda plus additional length. Additional length. Now, this is something we know, only then we can have this minimum distance from the point O where dark fringe is obtained. Now, how do we even look at this in phasors? See, this additional length we'll get by using phasors approach. So first we will take this S3 fellow. S3 fellow is here. If S3 fellow is in this way, then S2 fellow will travel 2 lambda plus additional length, right? So S2 fellow would be somewhere here like this, so that it will have to cover 120 degrees like this. It has to cover 120 degrees as point P moves to the point O. If this point P moves to the point O, then S2 will cover an angle of 120 degrees. Okay. Now S1 fellow, S1 fellow would be somewhat like this, which is having a phase angle should be like this 120 degrees, so that if all of them are 120 degrees, then we can expect them to cancel each other, and we can expect at that point P there is dark fringe. Okay, that's our logic. Now in order to have that, how do we analyze it? See, when point P moves to the point O, S2 will cover an angle 120 degrees, but S1 will cover an angle like here to this point as 240 degrees. So you know that S1 phasor will cover an angle 2 times of that angle swept by S2 fellow in order to reach a given point. Okay, so that is something which we have already learned. Now using that logic, what we can do? See, now it is almost solved. We can say that path difference between 2 to 3, it's given by d cos theta. We have already derived this. And path difference between 1 to 3 is 2d cos theta. See, either you can take this one and you can solve the first condition, or the second condition and solve. Suppose if you're taking the first condition and solving, then we can recognize like what is the phase difference. See, observe the phase difference between 2 to 3 is 2 lambda plus additional length. So 2 lambda corresponding to 2 pi 2 times, right? 2 times of 2 pi will correspond to 2 lambda plus additional phase. Additional phase is how much? See, S2 with respect to S3, it has an additional phase of 120 degrees plus 120 degrees. So it is 240 degrees. So it is 4 pi by 3. This is what we have as phase difference between 2 to 3 in reaching P. In reaching P. Now, if this is the story, then we can simplify this. This is going to be like delta phi in connection with lambda by 2 pi. So this will gives you the path difference between 2 to 3. So lambda by 2 pi as it is, this delta phi 2 3, that is going to be 2 times of 2 pi plus 4 pi by 3 times delta 2 3, that is nothing but d cos theta. So we can write lambda 2 plus 2 pi gone outside, so it is 2 by 3 times d cos theta. Now we can write this one as 8 by 3 lambda, which is equal to 3 lambda cos theta. Dear students, d is equal to 3 lambda given in the question. So you can simplify this and write cos theta is equal to 8 by 9. If cos theta is 8 by 9, then we can write this one as 81 minus 64. Then this is going to be root of 17. So we can write this tan theta as root 17 by 8. So where is this tan theta? Now this is the angle theta. So we are using tan theta from this triangle. You like however we did for the very first dark fringe, right? Like that. So tan theta is equal to x by d, but we know this is minimum now. So x minimum is going to be a root 17 by 8 times of d. This is what we have for x minimum, meaning you can use the first condition, you can derive like this. Suppose, no sir, I want to use the first source and the third source, then the part difference is 2d cos theta, and the corresponding phase you supposed to write, because it has already covered phi lambda, right? So you can write phi times of 2 pi because it has covered phi complete. wavelengths, then plus additional length. Additional length will be correspond to additional path, and that will create additional phase. This additional phase, how much? For S1 to S3, that is just 120 degrees. So 120 degrees correspond to 2 pi by 3. Like we can now write lambda by 2 pi times of delta phi 1 3 is equal to path difference between 1 3. So this is 2d cos theta, 2d cos theta, and here lambda by 2 pi times of phi phi plus 2 by, sorry, 1 by 3 times of 2 pi. So you can cancel 2 pi and 2 pi. So we can write it as lambda equals, this is 1516 by 3 equals 2d cos theta. So we can write it as 8 by 3 lambda equals d cos theta, and d is 3 lambda cos theta. It's given in the question. So lambda lambda getting cancelled out. It is 8 by 9 cos theta. So from this you can observe that this equation and this equation are one and the same. So if you solve for tan theta, you will get the same answer. Of course, the minimum value of x is given by root of 17 by 8 times of t. So I hope you understood this problem, and if you have any doubts, please put that in the comment section. Thank you, everyone.